Hi guys, so today we'll continue our AP Physics 1 solutions. To this time we're going over free response question 2 from Form J. And free response question 2 tests our ability to transfer our knowledge between visual, graphical, and uh, verbal representations as well as using equations. So that's why it's called the translation between representations question. This is the longest question on the test. So we're going to start with going over the scenario. So a block is sliding down a ramp with negligible friction, and it's the ramp is marked with 12 equal intervals of length, and the block is going to have three different types of energy. It's going to have two types of potential energy: the gravitational potential energy from its height, the elastic potential energy from the spring in the system, and there's the block's kinetic energy as it's moving. So that's why we have the block spring earth system, so we can track all of those and apply conservation of energy, since there's all three forms of energy are included and the total mechanical energy will stay the same. So the first part is asking us to draw energy bar charts to represent this conservation of energy at three different distances, and one of them is given to us, so we know which we include 12 units here because of 7 plus 2 plus 3 there. So the first one we're doing is x equals 0 when the block is at the very top. The block is released from rest. So because we know the block is at rest at this point, we can keep k at 0 because we know that the kinetic energy is going to be 0 when the object's at rest. So make sure you draw this solid line to represent k0. At both times 0 and 6, the spring is not compressed, it's at its relaxed state, so we can set the spring potential energy at 0. Since we have two energies set at 0 already, we can just set the gravitational potential energy to be 12 times E sub 0 because um, we know the total energy is 12 and the other energies are set at 0. So we can use conservation of energy here to determine that. And I'm just filling in the things outside here off screen, but you guys can see me explain the logic here as well. But the gravitational potential energy will scale with d. So with every increase in d, the gravitational potential energy will decrease. So that will lead us to 6e sub 0 for gravitational left at 6d. So we can fill that out quickly. I'm just filling it out slowly right now for the gravitational, and that leaves us with half of the energy, the total energy, to be in kinetic energy here. So we can fill out the rest with kinetic. And make sure that you'll see this in a moment, but if something is 0, you gotta draw a solid horizontal line at the 0 mark. So here's the part A answer that we were looking for. So you can see that at 0, the only thing is gravitational potential energy, which gets filled with 12, and it's half kinetic, half gravitational at 6. Part B is going to ask us to derive an equation for the spring constant. And it's telling us to start with conservation of energy. E initial equals E final. So initial would be at 0. So this means 1 half times m v squared initial plus, that's kinetic, gravitational conditional energy, mgh initial plus, cancel that, and then we have spring potential energy 1 half times k times x squared, and the spring is at its equilibrium, so we will set this to 0. We'll see this later. And then the same thing, but the final ones next. So we're going to just change this to final, and here too. And we can plug in values of v squared initial equals 0 because it's at rest, and v squared final is also 0, so because there's 0 kinetic energy in both places. And we can set x squared initial 0, and then h final equals 0. And then once we get all these 0 substitutions, we're left with mgh equals Um, and then we have to define h as well after this, and this would be 1/2 kx squared on this side. And then we can say h equals, we can use theta here. So we know the sine of this angle would be the vertical component that we're looking for h. So we can say 12d sine theta. And x would be 4d. So this leaves us with 12 mgd sine theta for initial equals 1/2 times k times 4d squared. And then this would be 12 mgd sine theta equals 8kd squared. And when we isolate for k, we should get k equals 3 times mg times sine theta over 2d, which is our answer. In part C, we're asked to do a graph of the energies, and we're going to need to get the total mechanical energy and the gravitational potential energy at each position from the once the spring starts getting affected here. So because of conservation of energy in this system, the total mechanical energy will just be a straight line at 12E0 because we know that's when all energy is. And the gravitational will just vary alongside the height. So it'll be 0 at 12D and then it'll get to go to 4E0 there. We can ensure that it's always going to be 12 and use it to find kinetic energy at other points. So I can just copy paste my graph here for part C. And you can see that it's a straight line for total mechanical and then for gravitational the other one. So you would label this as I'll just label it that way. Total mechanical energy is horizontal line. Bottom is gravitational potential energy with a negative slope. And in part D, we're asked to make a claim with a relevant justification. So we will have to see if the velocity at this point on the graph is greater or less than at 90 is greater than or less than the velocity at 8d. So we can see that it's very slightly the gravitational potential energy plus the spring potential energy at 8d is 4.0, and it's slightly less than that because you decrease the gravitational by 1 but increase the spring by just slightly less than 1. That means there's going to be more kinetic energy at the at 90 than 8d, which corresponds because kinetic energy is proportional to the square of velocity. That means a higher velocity at 90. So I'll just write it out here. V of 90. No. V of 90 is greater than V of 8 at 8d. The according this claim is consistent with the energy curves drawn in part C because it shows that total mechanical energy is conserved at 12E0 across all distances. And since we're going to talk about the sum of potential energies at x equals 8d is 4E sub 0, and the sum of potential energies at x equals 90 is slightly less than 4E sub 0. Because total mechanical energy remains constant at all distances, this results in the block having more kinetic energy at x equals 90 than it does at x equals 80. And since kinetic energy is proportional to the square of velocity, the block will therefore have a higher velocity at x equals 90 than x equals 80. So that's a pretty long justification here. I'm guessing you just have to do the kinetic energy velocity connection and just say why it has more kinetic energy, and then you'll be good. And do notice that the graph, it's a very slight difference, but it does matter. We saw this in the AP Chem exam with pH, but in science, it's really important to be precise and specific. So that's question 2. See you next time with question 3 with the experimental design.